Right, so the title is slightly different than what I wrote originally. I added the word pathwise because I think a lot of us are used to time reversal in a certain way, and although that way will appear, I want to really emphasize the other path, time reversal, which will be done in a pathwise manner. And since I have like 30 minutes or so, I thought to choose a topic which could both be interesting and hopefully I can cover all the details and all the motivation and almost everything in 30 minutes. So that's a challenge for me. But we'll see if I do it. And yeah, this is a joint work with Tom Courted from Berkeley and Max Fatih from Paris. So, okay, I really want to talk about reversed coupling. But before we do that, I want to speak a bit before that on standard couplings or forward couplings. And hopefully that will also connect to many of the different talks we heard today and in the previous days. But let's start with some motivation, at least motivation for me for coupling. And this is an inequality which appeared in at least 2 talks, I think, during the workshop, the Talagrand transport entropy inequality. Right, and at this point, I probably don't have to explain what Wasserstein-Dürr is or entropy, right? And the Talagrand inequality basically allows you to bound the Wasserstein distance to the standard Gaussian by relative entropy or KL divergence to the standard Gaussian, right? And this is an extremely fundamental inequality. I mean, it gives you the Gaussian dimension free concentration, but also with respect to optimal transport, right? It gives you Wasserstein contraction along heat flows, and it is related to displacement convexity of entropy. Now, I mean, if you go back to Talagrand's original proof from '96, then the proof is really beautiful, right? He proves it in dimension 1. As we've seen in dimension 1, optimal transport is easy. Everything is explicit. You get a one-dimensional inequality. You can just plot and check that it's correct. Then the main ingredient is to show that this inequality tensorizes. So if you prove it in dimension 1, you get it for any other dimension, right? So that's a beautiful proof. But one remark I want to make is that, I mean, if you want to prove that inequality, you don't really need to find the optimal coupling, right? You could, in principle, prove it for any other coupling, right? Replace here W2 with the square deviation of any other coupling, and you'll get a better inequality. Okay, so you can try to find other proofs by looking for other couplings. Of course, this inequality is sharp, right? The constant 2 cannot be improved. There are equality cases, basically translated Gaussians. So in that case, you have to work with the optimal coupling. So with that in mind, I want to show a different, very, very elegant proof of the Talagrand inequality. And this is due to Lehec from 10 years ago. So I want to give minimal background. This is the only place where I won't give all the details. But if you have a measure on RD, I mean, what we've seen in several talks is that, well, you can construct an SDE, right, filtered with a standard Brownian motion, such that at time 1, it has the law of mu. Okay, you can construct that inequality in many different ways, right, where VT is some adapted drift. But there's a special choice of that drift. It's called the Follmer drift. It goes back to the work of Follmer in the 80s, which has several nice properties. The most important property, which shows why it should be connected to the Talagrand inequality, is that its energy along time equals the entropy of mu with respect to the standard Gaussian, right? So just to make a comment here, xt is just a shift of the standard Brownian motion, right? It is absolutely continuous. You can measure the entropy of that process with respect to the Brownian motion just by finding the density, taking the logarithm and integrating, right? You can find the density by Girsanov's theorem, and this is exactly the term you get. So this is the entropy between the entire process and the Brownian motion. What Follmer tells us is that this is actually equal to the entropy between the endpoints. Okay? So you have a clear inequality in one direction, but then you actually get an equality. So that's one interesting property. And well, another interesting property that we use is that this VT, the drift itself, turns out to be a martingale, right? It is optimal in some sense. So, I mean, at least ideologically, it has to be a martingale. Those are the only two things I care about. But I can also tell you that it is very explicit, right? It is, I mean, it looks like a bus martingale in some sense. You can see that the process xt actually has a law of a Brownian bridge, at least when you condition on the x point x1, the endpoint x1, right? Which again explains why entropy only depends on the endpoints. And I mean, it has tons of other nice properties. For example, if you just integrate it at time one and not along the entire path, you get the Fisher information. So you can also use it for many other things. But for now, I'll only care about the first two things and just the fact that it's a martingale. Okay, those are the only two properties I need. Here is a proof of Lagrange inequality. Let's take our Brownian motion. At time one, it has the law of the standard Gaussian. Let's take the process x1. At time one, it has the law of mu. Right, so that gives us some coupling. That doesn't have to be the optimal coupling, but it bounds from above the Wasserstein distance. Now, the only difference between the Brownian motion and the process x is in the drift. It's a shifted Brownian motion. So, I mean, that's an equality. Well, we can just use Jensen's inequality, take the norm inside the integral. And because that thing encodes entropy, this is exactly what we got, right? So it's a two-line. I could squeeze it into a single line. Right, very easy proof. And I'll make another comment here, is that, well, in principle, I could take two processes. I don't know. Take the same Brownian motion. One has the Vollmer drift for one measure, the second one has a Vollmer drift for the other measure. I get some other coupling between two measures, but I can use that, for example, to recover the Bakry-Emery criterion. Right? So I can take the same Brownian motion, get some coupling between measures, and prove that the same Lagrange inequality still holds if instead of the standard Gaussian, you take some measure which is strongly log concave, for example. Right? So that is what I would call a forward coupling or a linear coupling. Maybe to make another mention about the Vollmer drift, one way to characterize it is through a variational formula. Right? And in this variational formula, we try to optimize over all adapted drifts, such that when we add them to the Brownian motion, then at time one, we get the measure mu. Right? And in some sense, this is an adapted optimal transport problem. Right? Without requiring UT to be adapted, we are looking for all shifts, could be anticipative, which couple the Brownian motion to some other process which has a predetermined law at time one. Right? Where we have the constraint that that the difference between the two couplings has to lie on the space of processes with finite variation. Right? That's the natural metric on the winner space. Right? That would give the actual Wasserstein distance in that case. But we are restricting our processes to those which are adapted. That gives the adapted Wasserstein version. So one way to interpret the Lagrange inequality is simply that adapted Wasserstein is always bigger than Wasserstein, right? Because we are optimizing over a smaller space. Okay. I want to give one other example of such a coupling. Right, so let's look at that case here. Well, suppose we have two measures now, mu and nu, none of them is Gaussian. Let's take two processes, one with respect to mu, and the other one is with respect to nu. Right, so very similar to what we had here, but the main difference is that here I chose the two Brownian motion to be the same, but we can choose the same, now we can take two Brownian motions which are different than one another. They're independent. So the best thing we can do with independent processors or independent variables is convolve them, right? In that case, we can take, well, x1, which has a log of mu at time 1, x1 with the log mu at time 1, they're independent, we can convolve them, right? Take their, well, normalized means. That thing is simply equal to, on one hand, just the convolution of the Brownian motions, which is again a Brownian motion. And on the other hand, it's an integral over those things. Right? It's an integral over the convolution of the drifts. But the point is that that is still a process. It is adapted with respect to the filtration of the joint filtration of the two Brownian motions. At time 1, it has exactly this scaled law of the convolution of mu and nu. And we chose the Follmer drift to be the optimal one over all the couplings which satisfy that constraint of having the same law. Right? So that should tell us that the entropy of the convolution is bounded from above by the energy of that drift. But because the Brownian motions are independent, those guys are also independent. We can simply split everything we see here. And if you follow everything, then you get an expression here which involves separately the entropy of mu with respect to the Gaussian and the entropy of mu with respect to the Gaussian. Yeah. On, yeah. Well, here, Vt is not deterministic. It's a diffusion coefficient, right? So it depends on x, right? Sorry? Yeah. Why don't I have what? Oh, of course, I should have an expectation. Here? What am I missing?
It looks like the painting on the right. How do I understand that?
I'm kind of bad at it, but I think that this is what you get by addition. Right? I mean, right? It's you simply write the first one. Yes, along xt. Right. It's a diffusion coefficient. I mean, yeah, it's a vector field, right? So it depends on x at time t. Right. I mean, yeah. Sorry. Here. Right, so you get this inequality between entropies, and this is the Shannon-Stam inequality, or the entropy power inequality, right? Which tells you that convolution can only reduce entropy. You cannot create more info. Well, can only reduce relative entropy. Okay. So we had two different couplings. We had two different applications. And there is one thing which was in common here. Right, so just to clarify, the two extreme cases here is we took two different Brownian motions. In one case, we took them to be independent, and we got one type of an inequality. And in the other case, we took them to be the same. Right, we coupled them in a trivial way, but both of them are kind of trivial couplings, and we got a different type of inequality. And you can think about many different ways to do that, right? Maybe you can think about having some ambient Brownian motion and taking the first one to be some linear mapping of that Brownian motion, and then taking the second one to be some other linear mapping of that Brownian motion. Right, so if you take those to be orthogonal projections, for example, then that would give you the case of independence. If you take those to be identity, then that will give you the case of having the same Brownian motion. Right, specifically, you can think about that case. And if you follow that thing, you get a spectrum of inequalities. Right? And you get a lot of tools to study those inequalities, and those have been studied a lot in the literature. You get a very general bunch of forward reverse plus complete inequalities. Okay? So that's I mean, that's kind of the motivation up to now about linear couplings or forward couplings and what you can do with them. So for the second part, here is a slight variation of the Talagrand inequality. Right, in that variation, so that's an inequality that Max Petit proved in 2018. In this variation, you look at the Wasserstein distance between two measures, mu and nu. One of them needs to be centered, but that's not super important for the discussion. And it turns out that for any two measures with the centering condition, the Wasserstein distance is bounded from above by 2 times the entropy of the first one with respect to the standard Gaussian, plus twice the entropy of the second one with respect to the standard Gaussian. Okay, so to make some comments, first, this is formally stronger than Talagrand, right? If I take the second measure to be the standard Gaussian, and I get Wasserstein to the standard Gaussian, and the second entropy is just 0, right? So it's formally stronger. If this is the first time you're seeing this inequality, then you should not be very impressed, right? Because if you just take the original Talagrand inequality and you apply the triangle inequality, then, well, you get a factor of 4 here instead of a factor of 2, right? Simply because you have a square, right? When you're squaring the triangle inequality, you lose a factor of 2. So it seems like to be quantitatively very, very similar, but there are at least 2 qualitative reasons which makes this very, very different than the Talagrand inequality. The first one I'm going to explain exactly now, and then I'll need to say some few words to explain the second one. And this is something which I don't completely understand. I mean, I can explain the reason why they're different. I don't understand what's happening. So, I mean, if anyone has any thoughts, I'm happy to listen and to hear. So one reason why this is qualitatively different than the Talagrand inequality is that by duality, this turns out to be formally equivalent to the Blaschke-Santalot inequality from convex geometry. Right? So Blaschke-Santalot tells us if we take any 2 measurable functions and one of them needs to be centered, because that's the exact same condition we have in the symmetrized inequality, which satisfies basically the duality conditions for Wasserstein, then you get a bound of on their integrals. Right? And the bound is 2 pi to the n, which should be familiar to everyone. It's the square of the normalizing constant for the Gaussian. Right? So, I mean, this is maximized when you take f to be quadratic and g to be compatibly quadratic. Okay, right. So this is extremely fundamental in convex geometry. Turns out to be the dual form of that inequality, right? Which is definitely not true with the constant form. Right? So that turns out to be a big difference. Here is another big difference. Oh, yeah, and just the same as with the Talagrand inequality, it would be enough to show the existence of any valid coupling for the inequality. Right, so I mean, it would make sense to try and repeat Lehec's proofs for Talagrand and prove it in the same straightforward way. Right, so what we would like to do is to take 2 processes with 2 Vollmer drifts driven by 2 Brownian motion, couple the 2 Brownian motion in some way, such that we get a coupling and we can measure the distance at time 1, right? So that is a coupling between the endpoint of the first process and the endpoint of the second process. So it's a bound on the Wasserstein distance. Well, I'm kind of cheating in that equality here. I'll explain exactly why. But, right, that thing has a Brownian motion at time 1 plus the drift here. That thing has a Brownian motion plus the drift here. So we'll just get their differences. Probably I need a dt here. Huh? Well, I didn't say anything. So that's why I'm cheating, right? So, I mean, that would make sense if I'm taking the 2 Brownian motion to not be the same, but to at least have the same endpoints. Right? And then I won't get into details, but that's the best thing you could do. Right? So otherwise I'll have another term here. Right? So or I just won't fit on the entire slide. Okay, so we get something like that, and then the question is, does that thing split as the sum of the two drifts, which will exactly give me the entropies, right? And this is not immediate because, well, I still have the cross term. There should maybe be some correlation between the drifts at time t, and it's, depending on how I couple the Brownian motions, right? So I wrote here that we must have B1 is equal to, then we must have that the endpoints are the same. Must is kind of a strong word, but if we want it to be true for the case where both measures are the standard Gaussian, then this is definitely a necessary condition, also sufficient, right? But the main point is that if you repeat the calculations and you take the same case as the Talagran proof and you take the two Brownian motions to be the same, then the calculations don't go through, right? In the sense that you don't get the correct inequality. And you can say a bit more. This is actually something that you can prove. There exists no linear coupling which produces that inequality, which produces the correct inequality that we want. Right? Linear coupling means two Brownian motions which can be adapted to the same filtration. Right? So that's another qualitative difference between the two inequalities. One of them feels okay with joint filtrations, and the other one simply doesn't go through. Again, I don't understand it. Right? So maybe there is another type of coupling. And this is where the reverse coupling from the title kicks in. So we want a coupling which, right, at least will give us that property that there is no joint filtration, but the two Brownian motions agree at time one. So here is, if you open Wikipedia and you look Brownian motion properties, this is like one of the first four, right? If you take a Brownian motion and you reverse the path, you get a different Brownian motion, which starts out from 0. Right? It has the same quadratic variation of the Brownian motion. It starts out from 0, and at time 1, it has the exact same point as the original Brownian motion. But it's definitely not adapted to the same filtration, right? And maybe to show it a bit, right? Suppose we have a Brownian motion, and I guess this is the forward arrow of time. The reverse Brownian motion starts from the end. So at the beginning, we see independent Brownian motions, right? The past is independent from the future. But at one point in time, well, actually after exactly half units of times, they will overshoot one another, and then the processes will become dependent, but not in a trivial way, or in a very non-trivial way, actually. But we will still have a trivial proof of the symmetrized Talagran inequality, right? Because here is the main point about the reverse coupling. Suppose we have two adapted processes. One which is adapted to the original Brownian motion, and the second one which is adapted to the reverse Brownian motion. It is true that the processes are not independent, but if you look at any fixed point in time, that process is right? If that process goes all the way up to time t, then it is dependent from anything that the other process does up to time 1 minus t. Right? Those two Brownian motions are independent to each other until they meet. So now going back to the inequality we wanted to get a bound on that square difference of the drifts. There's an easy trick in integration, where if you want to integrate Vt between 0 and 1, well, it's deterministically equal to the same integral when you integrate from 1 to 0. So I can simply replace one of those integrals. Take the same Jensen inequality to put the norm inside. Open up basically the norm. On one hand, we get the energy of the first step process. In the second one, we get the energy of the second process. We can reverse time back now, it doesn't matter. And in the third one, we get the cross terms. But we get the cross terms between the process at time t and the process at the drift at time 1 minus t. So they are independent. We can split it. Right? And now this would be awesome if one of the processes had 0 expectation. Right? So this will completely vanish. Right? So when does it vanish? Well, we have our 2 processes. I mentioned that one of them needs to be centered. And I also mentioned that the drifts are a martingale. Right? So at any time, the drift has the same expectation as time 1. And if you integrate it, if you integrate the expectation between time 0 and time 1, you get the same expectation of the measure. So at any time, the drift for the centered measure has expectation 0, right? And then that term completely disappears. And we get the exact same inequality we wanted, right? So we can take the difference between the 2 couplings, it's a difference between the 2 drifts, and because they are adapted to reverse filtrations, the cross term simply disappears, right? So we are left with the thing we wanted, which I wrote the word equivalently, and this is not correct, right? It implies the symmetrized Talagrand inequality, but it actually implies something stronger than the symmetrized Talagrand inequality. It implies that there is a coupling, which in general is not the optimal coupling, which is still bounded by the entropies of the 2, of the sum of the entropies. Any questions? So I feel compelled to say a bit more, because I mean, this is a very easy, I mean, even though it took us a long time to actually think about it that way. There's another slightly more complicated way to think about what's going on here. And I mean, this kind of shows you that you kind of need a sort of tools for a reverse Ito calculus, right? It's true that, well, when you take the reverse Brownian motion, it is a backwards martingale with respect to the filtration of the original Brownian motion, but you need to have a calculus which allows you to handle at the same time both processes which are adapted to one filtration and processes which are adapted to the reverse filtration, right? And somehow here this formulation with the drifts allow us to completely bypass that need because we simply have independence. But there's another more complicated way to think about it, which I think should be useful for other things. And this is the following thing. I mean, if we have any random variable on the Wiener space, suppose the endpoint of those processes, right, by the martingale representation theorem, it has a martingale representation with respect to the Brownian motion, right? So Ft is some diffusion coefficient, which gives us the martingale representation. But by the martingale representation theorem, it also has a martingale representation with respect to any other Brownian motion on the Wiener space. Right? So it also has a martingale representation with respect to the reverse Brownian motion, which will give it another different diffusion coefficient. And you can ask, how are those 2 things, how are those 2 diffusion coefficients related? Like, it's not clear that there should be any meaningful relationship actually between them because the Brownian motions are completely different. So one observation here is that they have matching first moments, right? If you look at the expectation of the first coefficient at time t, it has the exact same expectation as the other coefficient in the reverse time scale. And this is a, you know, this is a very easy consequence of the Clark-O'Cone formula, which gives you an explicit representation of in the martingale representation theorem. And if you're not a fan of Maliavini calculus, then you can also do it using standard isoisometry and just add 2 lines to that identity here. So, I mean, this would kind of suggest that there's a big connection between the processes, but it turns out that this is where the relationship stops. So they have the same expectations, they don't have the same second moments. But they satisfy some inequality with respect to the second moment, right? If you look at the second moment and you integrate it in the future, that thing will always be larger than the integrated second moment with respect to the past of the other representation. Right? This is not a very hard thing to show. You can just try to show it because you have the two like the two independencies between the filtration at a given time t, right? And you can simply use that to do an orthogonal projection. And this is what you get. But by coupling those two things together, you get an inequality with respect to those things, right? When you integrate them over in the future with respect to the past. Now, this should look familiar maybe with respect to other talks we had earlier today, right? This is what we get. This is what you're trying to optimize for the bus, for the bus problem, right? And it turns out that there's a very well explicit, but again, not something which I completely understand. There's a connection with that with respect to the adapted Wasserstein distance in that case, which for the bus problem, you wanted to minimize that thing over all coefficients. And it turns out that, at least for the specific case, this should be a standard Gaussian, where we are trying to integrate things, we are trying to measure, well, distances with respect to the standard Gaussian. You can optimize over the same expression, but you need to reweigh the quadratic variation. Thank you. And to reweigh the quadratic variation in a way which makes it much larger as you become desperate and reach the endpoint. Right. So you can use all of those things I just said to get a more complicated proof of the symmetrized Lagrange inequality, simply because all of those things express entropy and they also express Wasserstein distance. But for me, at least, it's a bit more revealing. Okay, and I'll maybe end with a few comments. So, I mean, it's a coupling. It's definitely not a distance, right? When we took the trivial coupling here, it's very clear that if X and Y have the same laws, then this will, I mean, they will have the exact same terminal points. So it defines some distance. For the reverse coupling, if you take the same processes, if you take the same laws, there's absolutely no reason for them to end at the exact same point, just the same points will have the same laws, but it will be different, right? So definitely it's not true that, that the difference is zero almost surely. And unless both mu and mu are standard Gaussians, and in that case, well, I mean, you're not really doing anything. I mean, that's the starting point where we condition them to have the same endpoints. Right? So it's not a distance, but it turns out that in the symmetrized Lagrange inequality, there are some non-trivial equality cases. Right? The only equality cases are Gaussians which have compatible variances. Right? So you want to have a Gaussian with variance A for mu and a Gaussian with variance 1 over A for nu. But we know that our coupling works for the symmetrized Lagrange inequality. So it has to achieve an equality here, which means that the coupling which comes from the reverse Brownian motion is the optimal, well, it has the value of the optimal coupling, which is weird. Right? It's not clear why that coupling, which is very nonlinear in the end, right, should achieve that optimal coupling. Okay, and another point for thought is, in principle, here I could take any number of different measures, take the same Brownian motion for each one of those measures and get a multi-marginal coupling. And then there's a lot of things that you would be able to do with that in principle. But here, if I have 3 measures, I can take one Brownian motion for the first one, I can reverse the Brownian motion for the second one, and I'm stuck for the third one. Right? So the question is, how can I reverse time more than one? And this is not clear. So I mean, this is not a bug. It's a feature of that coupling, but maybe there's a way to generalize it further to get more generalized couplings. Okay, and This is mostly what I wanted to say, so thank you.